Okay. I think, yeah, we are done with setting up for the class. So those who are attending online, are you able to hear me?
Yes,
Yes,
sir.
sir.
Okay,
And
nice.
I see the board, sir.
You can see the board also, right? Okay, good.
Is this recorded?
Yes, it is.
Okay, thank you, sir.
Okay, can you see the slides?
Yes, sir.
Yes, sir.
Okay. All right. I guess then now we can start. Sure. So, yeah, so I guess you're already familiar with the syllabus for the course, right? I think I shared that with you. And any questions on, I think the evaluation scheme also I shared, right? So it's like, how much is it? 40% for exam, maybe like 2 exams, then 20% for assignment, and some 40% for project. Something like that, right? So tentatively, we can have it like this. We need no mic needed, right? This not required, right? Okay, so yeah, so the now we cannot make it 3 credits, it will be 2 credits. Yeah. Yeah. So at this point, we cannot change it. Maybe we'll see next year. Yeah, so yeah, basically, this course we will be dealing with how to look at all these data analysis from a Bayesian perspective, and we'll see what it means. And you see this something written here? You know, in which language is it written? I mean, it's not English, right? Which language, probably? So, Latin? Okay, even I'm not sure. Latin or Greek, something like that, right? Any idea what it means? I think I also forgot what it means. But any guess? Something related to posterior and prior, right? I guess it means every day is a disciple of previous day. Okay, every day you learn something, and you can see that, okay, next day you make use of what you have learned. So it's a disciple of previous day. And that's fundamentally the idea behind Bayesian learning, Bayesian data analysis, where you keep learning things and you make use of what you have learned earlier while solving some new problem through something we will be discussing something called prior. Okay. Okay, so this is basically the philosophy that we are going to follow. So we keep learning, and whenever some new problem comes, we solve that problem by making use of what we have already learned. That is fundamentally the philosophy behind Bayesian learning. And this is how the human learning also works, right? In humans also, we keep learning over time, and whenever some new problem comes, we make use of our already existing knowledge in solving that new problem. Right? So, and this is how the human can generalize well to some unseen task. So if you look at the way the state-of-the-art models in machine learning, deep learning, so they all require huge amount of data to learn something, to solve a particular task. For example, you probably are aware of this picture, right? What's this about? This is this AlphaGo, right? This guy is Lee Sedol. Right? Lee Sedol, well, I think in 2016, around 2016, I guess. DeepMind, they came up with this Go playing machine, which is called AlphaGo, right? And apparently, uh, this game Go, yeah, the Go game. Well, it's actually something similar to chess, but much simpler than chess. The kind of rules that are used is much simpler. The type of pieces that are used is maybe just one or two type of pieces and nothing more than that. So it's not as complex as chess, but it it the, see, but it was very, very difficult for somebody to develop a machine which can beat humans in the game of Go, unlike in the game of chess. And there are reasons why it is the case, because the number of possible moves from any particular board position is very, very large compared to chess. So it was maybe like 300 or 400 different moves are possible from any particular board position. And all these algorithms people have developed earlier, which is based upon search technique, where you search all possible moves and choose the right moves. It didn't work in this game of Go. Okay, so you may have heard of this what is it? Deep Blue, the one which was developed to play chess, or which beat Gary Kasparov in 1990s. Deep Blue, right? Yeah, so Deep Blue was developed in 1994, and it managed to beat that then legendary chess player Gary Kasparov in 1994. But it took more than 20 years for somebody to develop a machine which can beat a human champion in this game like Go. Apparently, though, they managed to develop this machine by making use of deep learning techniques, reinforcement learning techniques, and they played maybe like millions of games to make these machine learn how to beat a opponent. So, ultimately the machine learned some rules, learned some idea how to play this game by playing millions of games. But maybe a human will just play maybe like few thousand games and will be able to attain that level of expertise without playing too many games. So they make use of some additional knowledge they have from solving several different tasks, and they bring that additional knowledge in solving any particular task, so they don't need large amount of data to learn anything or to solve something. So we want machines which are as capable as humans, right? It's not just enough that the machines are there which is capable of doing what humans are capable of doing, but we want machines which are still better in terms of data efficiency, parameter efficiency, etc. So yeah, this is something from some accident which has happened to a Tesla vehicle. It was in autopilot mode, and it was unable to distinguish between some blue truck and sky. Maybe there was a blue truck, and it thought that is the sky, and it just rammed into that machine, and truck and accident happened. So these kind of situations arise where in many real world applications you have to deal with some situations which you have not seen before, right? So in typical machine learning, deep learning, how do you do? Like you train the model on some data, training data, and then you deploy that model. And at the test time, you will be seeing a lot of data, and you will be making some decision for the data that you will be seeing at the test time. So at test time, it may happen that you will encounter data points which are not you have not seen during the training time, and you should be able to predict well on those data. That is what we call generalization performance. But many of these machine learning, deep learning algorithms assume that the training time distribution, test time distributions are similar. But it could also happen that at test time you will encounter data which is slightly out of distribution, and you still want to make a good decision, and you don't want to make some overconfident wrong predictions which can lead to these kind of accidents. So this is especially important for several real-world applications. Nowadays, we are using deep learning, machine learning models for several real-world applications like autonomous navigation, healthcare. And it is very, very crucial that these deep learning, machine learning models are know how much confident they are about their predictions. So it's important that they don't make some overconfident wrong predictions, which can lead to these kind of accidents and very, very risky situations like this. So we want to develop very safe artificial intelligence applications where the model does not make such kind of overconfident predictions if it encounters some slightly out of distribution data, right? So rather, if the model can alert the driver, if the model is not able to clearly understand the data, if it can alert the driver and if the driver makes the decision instead of model making the decision, these kind of situations can be avoided, right? So that's what we mean by safe artificial intelligence applications. And this aspect is something we call uncertainty in decision making. So how uncertain the model is in making a decision and how well the model can capture that uncertainty in the data. So we want models which is capable of capturing that uncertainty and make good decisions rather than making some wrong decisions. Okay, here's another example of this issue that I have mentioned. So for instance, this is what we have observed experimentally with many deep learning models. So you train all these deep learning models on different type of dog images, and you give the image of a cat and ask, what type of dog it is. It may end up predicting some type of dog with very high confidence, even though this image is that of a cat and it has nothing to do with the different type of dog images it has been trained on. So this inability of the model to model this kind of situation out of distribution data is something very, very risky when it comes to real world applications. And we want the models to capture these kind of situations well, right? And all these are leading us to these Bayesian learning principles and Bayesian learning approaches, which will be able to let model able to understand the data well, the situations well, and capture these kind of situations. We will see how we can do that using Bayesian learning. Yeah, so yeah, these are some of the real world motivations why this uncertainty modeling is important, why developing safe artificial intelligence applications are important, and why attaining a human level performance is important, and how we will see how Bayesian learning paradigms can help in achieving all this. So now I will just give you conceptually what is the idea behind the Bayesian learning. So we will do it through one example. Okay, so here is some program, TV program, where there is one person will there is somebody who will be asking questions to some participants and try to guess the participant have in his mind. Okay, so the participant will be thinking about some person, and this interviewer will ask some questions to that person, some kind of yes or no questions, and he will try to guess the name of the person this participant is thinking about, right? Maybe we can try to play that game, and let's see if we will be able to find somebody I am thinking about. Okay, so let me just give me a few seconds. Let me think about somebody. Okay, I thought about somebody. Yes. So maybe you can ask some yes or no kind of questions, and I can give you like how many chances you want. 2 much? 5? How many chances you want first? 7 or 5? 5, right? Maybe you will find out in 2 chances itself. Okay, 5 only. Yes. What is the question? No. I know you will ask this. So you are going to ask this. So no, this no. Anybody online want to ask any question?
And like, what's the favorite sport of the person?
You should ask only yes or no question.
Is the
What's the
favorite
question?
sport cricket? Is the favorite sport cricket of the person?
Okay, the question is the favorite sport cricket? Well, is the favorite sport cricket? How do I know that? Well, I don't know.
Is the person from Hollywood or Bollywood?
Okay, the third question is the person from Hollywood or Bollywood? Hollywood or Bollywood? Okay. No, no. Who want to ask fourth question? Maybe like somebody from here. You see the person? Every day? No. Okay, ask yes or no. What is it? The question is he a male? Yes. Okay, I will give more chances to you. Okay, fine. Okay, the question is he a scientist? Okay, yes, he's a scientist. Okay, yes. Has he worked on RNN and transformer? Okay, has he worked on RNN and transformer? No, no.
Has he worked
Okay.
for ISRO?
Okay, eighth question, has he worked for ISRO? No. Huh? Is he alive? That somebody asked, right? No? Okay, yes, he is alive. He's alive. Okay, last question. This time I'm going to win. Last question. Why? What do you want to ask? I mean, you're a citizen? No. Okay, over. So it's our director, BS Mode. Okay, sorry. But yeah, he's somebody you all know, right? It's fine to guess him, right? Okay, fine. All right. So no, now let us see what was happening here, right? So initially, there are so many different possibilities, and some people use some prior knowledge and try to ask some question based upon that prior knowledge. But anyway, there are a lot of possibilities, and once some question is asked, that all those possible spaces comes down, right? And now you may have some reduced set of spaces, possible set of answers, right? And you will be asking one more question, and that will further reduce the space of all possible answers. So at every question, you gain some information, and that will reduce the possible set of answers, and finally, eventually, you may arrive at some particular answer, right? In this case, it couldn't, but it could happen. Say probably you may need more data points in this case, right? So if you had the chance to ask more questions, maybe you will end up in this answer. So that is the idea that will be followed in the Bayesian learning, where you initially you think that there are so many different possible solutions out there. Okay, maybe you may reduce that set of all possible solutions using some prior, but when you see a data point, you update that set of possible solution space, and you keep on updating that, and it eventually you will end up finding some set of possible solutions which is more accurately describing your data. That is the kind of an idea that is followed by the Bayesian learning when you apply it for machine learning or data analysis, etc. So I can just try out another game, something similar to this, but this time you are definitely going to give the answer. Okay, so here now instead of thinking about a person, what I have in my mind now is some concept. I'm thinking about some concept. Okay, some concept. So some concept means it could be like set of all even numbers, set of all odd numbers, powers of 2, powers of 4, then something like that, some concept. Okay. So what I'm going to do is that I'm give you some observation from that concept, okay? Some number from that concept, and you have to guess, okay, what is that concept I'm thinking about. So the first observation is this number 16. So what do you think? What would be that concept I'm thinking about? Power of 2 is one possibility. Yeah, this is a power of 2. Something else? Okay, numbers ending with 6. Yes. two-digit numbers. Yes, two-digit numbers. Okay, so there are several possibilities, right? Maybe you are not able to clearly guess anything from this, so we'll give one more observation. Okay, the next observation is 8. So that means two-digit number, no. Ending in 6, no. Powers of 2, yes, powers of 2 is still there. What are the other possibilities? Multiples of 8, yes. Even numbers. Repeated division by 2. Ah, okay. Okay, sure. Okay, so these are the possibilities, right? So we'll see more observations. Repeated division by 2? No. Multiples of 8? No. Powers of 2? Yes. Anything else? Even numbers? Yes. Anything else? Factors of 16. Okay. 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 Then I'll give one more observation. Now factors of 16, right? So what could be it? Powers of 2. Okay, sure. Then it is, okay, it looks like powers of 2, right? But why not even numbers? It's all even numbers also, right? But why are you saying powers of 2 and not even numbers? Sorry? 6 is also, okay, 6 is an even number, but you don't see it here, right? The reasoning is this. Okay, why am I not seeing any even number which is not powers of 2? I'm only seeing powers of 2, but if it is some concept like even numbers, I should see some even numbers which are not powers of 2 also, which I'm not seeing here, right? So that possibly lead you to say, okay, it's going to be powers of 2, right? Yes, that's a nice idea. No, but no, there could be, yeah, these are the two possibilities we can finally arrive at. So we have rejected several different hypotheses, like it is going to be two-digit number or ending in 16, all those multiples of 8, all this we rejected. And finally, after seeing some solutions, we finally arrived at these two possible hypothesis space, powers of 2 and even numbers, right? So our initial possible hypothesis space or distribution of our possible hypothesis space was something else. But after seeing some observation, we keep updating that, and we kept on updating that, and finally, we have all our probability mass getting distributed across these two hypothesis space, right? What if I was considering a hypothesis like this? Powers of 2 except 32. I could have probably thought about something like that, right? And this data that you have seen, which consists of 16, 18 to 64, perfectly can belongs to this hypothesis also, right? But no, nobody thinks about such complex hypotheses, right? Nobody thinks about such complex hypotheses. But let's see first why we chose our answer as powers of 2 over something like even numbers, right? And let's say a mathematical reason why it is the case, right? So we have an intuitive reason why it is the case, because we didn't see any even numbers which are not powers of 2, right? And mathematically also we can see why that is the case, right? So if you look at, let's say, hypothesis H1, which is powers of 2, right? So what are the all possible powers of 2, let's say between 1 and 100? How many are there? How many numbers are there? 6, right? Yeah, there are 6. What are those values? 2, 4, 8, 15, 32, 64. Okay? 2, 4, 8, 16, 32, 64. 6. There are 6 possible values. And you're seeing, you see all these observations, 15, 8, 2, 64. And you can think of observing each of them as equally likely. Observing each of these values in this hypothesis space H1 is equally likely. So observing each of them has some probability like 1 by 6. So probability of observing these values 16, 8 to 64, assuming they are coming from this hypothesis space of powers of 2, is going to be something like 1 by 6 into 1 by 6 into 1 by 6 into 1 by 6, right? But when you consider this alternative hypothesis, which is better for even numbers, let's assume that we are considering even numbers between 1 and 100. So the number of possible such values, that possible values belong to this hypothesis space is 50, right? 2, 4, 6, 8, up to 50. So the possibility of seeing any particular observation is 1 by 50, and possibility of seeing these observations 16, 8 to 64 is 1 by 50 into 1 by 50, like that, which is going to be much smaller than seeing these observations, which is 1 by 6 into 1 by 6 into 1 by 6 into 1 by 6. So we can see that probability of seeing these observations, assuming they are coming from H2, is much smaller than probability of seeing these observations, assuming they are coming from H1. So we should favor H1. But what if I had considered H3, something like this, where I consider powers to accept 32? What do you think? Probability of seeing these observations given H3, is it going to be smaller than H1 or higher than H1? It's going to be higher than H1, right? So do you think you will favor some hypothesis like this over this one? This is a more accurate, correct fit than this one, right? Why? It's kind of a more general, right? People, is unnatural to think that somebody will think about some hypothesis like powers of 2 except 32, right? That's not natural. People never think like that. But that comes from some kind of a domain knowledge. It comes from a domain knowledge that normally people don't think like that. So we shouldn't give very high probability to a hypothesis like this. People don't think like that, right? So that's something which is coming from our domain knowledge, which unfortunately we won't be able to capture. If we are only looking at these figures. Okay? So if you are only looking at this figure, which is probability of seeing these observations given the hypothesis, in the Bayesian or probability, we call it as likelihood. The likelihood of seeing these observations given some hypothesis. If you're looking at the likelihood alone, the likelihood have favored something like H3 over something like H1, right? So the likelihood does not actually capture everything. It does not capture the real world or domain knowledge of some things. Okay? So we need to go some beyond likelihood to able to capture that aspect, and we end up correctly predicting H1 as our answer rather than something like H3. Okay, so how can we do that? So likelihood is not sufficient, because it may end up giving very high probability to some unnatural complex solutions hypothesis like H3, but no, which is not the real solution. Okay, so let's do something now. Let's try to put some. So what we said is that this is unnatural, right? This is unnatural. No, this is unlikely that somebody will consider a hypothesis based like this. So that we want some way to encode that domain knowledge, capture that domain knowledge. And what we can do is that we can have some kind of a prior probability distribution over all these hypotheses, which captures that, where we give very low probability to these kind of unnatural hypotheses and very high probability to some very commonly occurring hypothesis, right? So we can now bring that prior into picture. Okay. So this is the prior probability distribution that we now have, where we give a high probability distribution to some hypothesis like set of all even numbers or set of all odd numbers, because that's most naturally occurring hypothesis, and some kind of equal probability to all these multiples of 3, multiples of 4, some n's in 6, n's in 5, powers of 2, powers of 3, but very, very low probability to some very complex hypothesis like powers of 2 plus 37 or powers of 2 minus 32. Okay, so we can have some kind of a prior probability distribution over these hypotheses, which capture our domain knowledge that people are not going to think about these kind of complex hypotheses. Right. So now, what we can do is that we can combine that prior knowledge that we have with the observations, what we observe, right, and get a final outcome by combining them. Basically, you can think of just multiplying these two probabilities. So here in this figure, you assume that you only observe 16. Okay, so when you only observe 16, the probability of 16 given odd is going to be 0. Probability of 16 given even is going to be kind of something like this, which is going to be very small because the number of possible even numbers are very large, right? Cardinality of this set is large, so that probability is going to be small. And squares, okay? So that probability is higher because cardinality of this set is smaller. So probability of seeing 16 given squares is higher. So now if you look at powers of 2 also, it's have a very high probability here. So so even powers of 2 minus 32, it also have very high probability, right? So if you look at the likelihood is higher for some complex hypothesis like powers of 2 plus 37 or powers of 2 minus 32, as well as some of these other hypotheses that we are considering. And what we do now is that we multiply these prior probability that we have over this hypothesis with this probability, and we get this final probability distribution over this hypothesis space, where we can see that, okay, now this probability that you associate with these complex hypothesis has gone to 0 because we have considered this probability, prior probability over them to be very, very small, close to 0. So you multiply this with this likelihood, you end up getting this probability, which is going to be very, very close to 0. While the probability for something like, what is this? Powers of 4, right? Yeah, powers of 4 is kind of high. Powers of 2 is also reasonably high. Right? So, yeah, so this is what will happen when we multiply the prior distribution that we have with this likelihood and consider that as our final outcome, which we want to make use of for our decision making. Okay. So that will capture that domain knowledge that we have, and we don't end up predicting this unnatural hypothesis as our answer. And again, the same thing for this case where you have data 16, 8, 2, and 64. And you can see that, yeah, you end up getting very high probability for these powers of 2 hypotheses, where the probability for these complex hypotheses will be very small. And you end up finding, okay, saying this as your solution. So this is how, considering some kind of a prior knowledge, prior distribution, our no set of all possible solutions can be helpful. It can help you to get into your right solution through this prior. Yeah, so this demonstrate how the priors are kind of very, very effective. And that leads us to this fundamental theorem, that's the Bayes theorem, which we will be using all throughout the course. So the entire course is just about this single theorem, okay? Just about this single theorem. All that changes is discontinuity, prior, likelihood, and how you compute this posterior, P of theta given to. Otherwise, the entire course is on just this theorem. And we will see how this theorem and how we can bring all those machine learning, deep learning, every model that you know within this framework of this Bayes theorem. You will see, okay, this can be a something like a Bayes classifier, or can be a logistic regression or a linear regression, or can be a deep learning. All these models can be brought into this framework that we have here, which is described through the Bayes theorem. And we will be developing a Bayesian counterpart of all the models, machine learning models, deep learning models that you know in this class. Okay. So yeah, so I'll be assuming you know machine learning, deep learning. Is there anybody who haven't taken any course on machine learning? Okay, but you know the basics, right? Okay, then it should be good enough. Like, you know what is a linear regression, logistic regression, those things. Yeah. So I will not be discussing those algorithms in detail. I will be assuming you know linear regression, logistic regression. Then I'll be discussing how you can develop a Bayesian linear regression, Bayesian logistic regression, Bayesian ABS classifiers, Bayesian deep learning models, Bayesian neural networks, all that. Why is this looks very sleepy? You many times ignore that, right? You don't care about him, right? And since nobody is caring about him, he's feeling so sleepy, right? And you know why? This is half up and half down. So likelihood it is full up, this is full down. So you end up getting a posterior which is half up and half down, right? Now we will see, in real, we will see when we look at these models, you end up doing that, okay? You end up learning parameters which are somewhere in between the prior and likelihood. So that's what this means. So those are online. Any questions?
No, sir. Sir, on board, are you writing something? Actually, the part which is visible to us online is empty.
I'm not writing anything now. Yeah,
Okay,
I'm not writing anything now.
thank you.
Right. So here's an example to demonstrate how this Bayes theorem works for some small use cases. Okay. So all right. So okay, this is some example I created for an arbitrary situation. Like you go to some conference, you meet some people, and you talk to them, and the way they talk about some topics, you get an idea if they are from academy, if they are from industry, etc. Okay, so assume that you meet somebody and you are asking him which area are you working, and he's answering something like, I work on different verticals, aviation, pharmaceutical, all these. You talk about a lot of different terminologies, and immediately say that okay, he must be from industry. You see people talk about a lot of such terminologies. Okay, so this is one such example. Oh, sorry. I generally talk about this in regular class, and there are some online people here who are all from industry. They may have felt bad. I'm sorry for you. Uh, I hope you haven't heard this example. Okay, so if you think of some word like vertical and all, those kind of some terminologies, industry people uh, use that word a lot, and often 75% of the times you find that okay, people use this word. Well, in academia, they may don't use this word much, but in a general conference, when you attend, most of the people will be from academia, like 80% will be from academia, and just 20% will be from industry. So if you look at a priori, before talking to somebody, the probability that somebody that you are meeting is from industry, it is going to be something like zero point 0.2. And a priori, the probability that you meet somebody from academia is going to be something like 80%, 0.8, right? But now after talking to them, you talk to that person and you get these observations, data. What's a probability, assuming that that person talked this word vertical, what's the probability that this person is from industry, or the probability that this person is from academia? Okay. And if you want to find that, you can use Bayes theorem. Okay, you can use Bayes theorem to find that. And apparently you can, uh, consider this prior odds ratio, probability of industry to probability of academia as 0.2 is to 0.8. And assuming this word is being used by this person to whom you have talked to, this probability is going to be something like 0.75 to 0.15. So you multiply this likelihood and prior, you get something like 0.15 to 0.12. So the probability that the person is from industry is higher than the probability is from academic, right? So a priori, there is a higher probability that you meet somebody, the person you are meeting is from academia, but once you observe this, it changes, that the probability is higher that he's from industry. Yeah, this is one example of how to how the Bayes theorem can be useful. And who invented Bayes' theorem? Of course, Bayes, right? No? Then who? I forgot who is who. I think this is Bayes, right? I think this is Bayes, right? Anybody know Bayes? No, you can't recollect. All right. Who invented Bayes' theorem? Finding out the answer. Okay. Can you find out who it is? Okay. So Bayes' theorem is current form, like this, as we saw before. This theorem, Bayes' theorem in this form, is actually invented by Laplace. Okay? But the concept of Bayes' theorem is proposed by Bayes, and they are both contemporary. Okay? They are both contemporary. They independently find out this Bayes' theorem. And Bayes apparently gave this concept of Bayes' theorem that, okay, at that time they called it has something like inverse probability theorem and all. Because what you're trying to find out here, this is the inverse. You can think of this as the inverse of this likelihood that you are having here. So they call it as inverse probability theorem. And the idea of this was given by Bayes. And posthumously, after the death of Bayes, his friend published that idea, which I think it was in some, I don't know if I have it here. Yeah, I don't have it here. Yeah, published this idea, and his idea was motivated by this how to find causes from effects, and he conducted some experiments by dropping some ball, and he kept on performing this experiment and see if he can improve his belief about some aspect about this ball by dropping this ball experiment. So this idea of Bayes' theorem that we have in current form, that there is a prior belief, and you perform some experiments or you get some data and you update that prior belief to get some kind of posterior belief. That idea was apparently proposed by Bayes, and it was published after the death of Bayes. But the theorem, as we know now, was actually proposed by Laplace, and he used it for a lot of different real-world applications. Apparently, he used it to estimate the mass of some celestial object, like Mars or something, based upon the position of the Mars at different positions in the sky or over different days. So he treated that as the data, and then he tried to estimate the mass of Mars based upon that data using the Bayes theorem. And he used it for several other. Apparently, I think he was a very popular figure in 1700s in France or somewhere, and he was a famous popular statistician, and he used it for several data collected from birth of people, some death of some soldiers, several different data. He applied this Bayes theorem to estimate some beliefs. Okay? So this Bayes theorem was made popular by Laplace, and he is the one who proposed it in current form as we know now. And then we know that, okay, later Alan Turing, he also used this Bayes theorem in deciphering the German Enigma cipher during the World War II. Okay? So you can read about all this history of Bayes theorem in this link. They have a very nice history of all this Bayes theorem available in this link. And we still use Bayes theorem. for data analysis, for machine learning, for deep learning, for developing decision-making system is still used basically. So some people say it's the theorem which never dies. Okay, so in our course, so we use this Bayes theorem to develop Bayesian machine learning algorithms, Bayesian deep learning algorithms, right? So what change is happening is that, okay, this model that we will be using here to model our data, right? That model will be differing, like we will be using a regression model, classification model, and we will be then trying to estimate some kind of a posterior belief about different parameters of the model by using this Bayes theorem. So yeah, so the way fundamentally we are going to use the Bayes theorem is that, okay, so in every machine learning, deep learning model, we want to do a parameter estimation, right? And all of them do a point estimation of the parameters. We just try to find out that particular value of parameters, which can best explain the data by solving an optimization problem, right? But we'll see that in several situations, just having a single estimate of the parameters may not give you a very robust model, which will work for all the different situations. Rather, you need to learn some sort of a distribution over the parameters. And that distribution over the parameters, if you have some sort of a distribution over the parameters, that can lead to a very robust model, which can predict well on all the different situations. So the idea fundamentally is, okay, you start with some kind of a prior distribution of the parameters. So theta can be seen as some kind of parameters associated with, say, linear regression model, or a logistic regression model, or a neural network, or an A-Bayes classifier. Okay, it can be some parameters that are associated with all these models. So you start with some prior distribution over these parameters, prior belief over these parameters, and then you see how well the parameters are able to explain the data that you have. And on the basis of that, you update your belief using this Bayes theorem and get some kind of a posterior belief over your parameters. So the posterior belief will take into account how well the parameters are able to explain the data. And you learn some sort of a distribution over the data, which can distribution over the parameters, which will explain the data very well. So that is fundamentally what we are going to do in our course, and how we are going to do for different kind of models. Okay, we will be looking at all these different kind of models, and in some models, okay, we'll be able to estimate this posterior very, very easily. For certain models, we won't be able to estimate this posterior very easily, so we need to do some approximation techniques. So we want to find out an approximate posterior. So we will be discussing some approximation techniques like sampling techniques, Markov chain Monte Carlo techniques, or other type of sampling techniques, importance sampling, all that, and some inference techniques like variational inference, expectation propagation, Laplace approximation, all that. So we'll be discussing all those as well as part of our course. Okay, then we will also look at some recent models which has been proposed, including deep learning models, variational autoencoderers, diffusion models, all that, and how these principles can be used for optimization, like Bayesian optimization, active learning. So we look at all those topics also as a part of the course. Okay, so these are now some of the motivation that we already discussed. Like we want to develop safe artificial intelligence applications. And by safe artificial intelligence application, okay, we want them to model uncertainty. Uncertainty means if they encounter some out of distribution data, they should be able to identify that. They should be able to understand, okay, it is an out of distribution data, so I may not be able to make a correct prediction. So rather I let a human take a decision rather than I myself take some incorrect, wrong decision, right? So that is what we want to achieve. Maybe I'll just leave this slide for the time being and come back to this slide later. And there are several applications which can benefit from this uncertainty modeling. For example, here is an example where maybe like autonomous navigation, like there are autonomous navigation systems that we are developing, where the system want to detect the boundary between the road and footpath, or it has to distinguish between car and other pedestrians and other objects in the surroundings. So here in this example, a standard deep learning model might end up saying that, okay, there is a segment boundary which is going to be something like this. But apparently, the major issue here is that this glass, because of this glass, it's transparent, and it might end up missing. There is some uncertainty around this area, and there could be a segment boundary like this, as well as the segment boundaries could be something like this. But there is some uncertainty. Even as a human, sometimes we can end up missing because this kind of some kind of a transparent area, because this is the glass which is transparent. So we want our model to tell us, okay, there is some sort of an uncertainty around this area because it is glass and transparent. And this is what a Bayesian deep learning model will tell us. For instance, it can use these kind of, in addition to this segmentation boundaries, it can provide us areas where it is very uncertain about. And this picture shows that it's very uncertain about this region, and maybe like this region, but some high uncertainty exists around this region. So that additional information that it provides about its uncertainty can be useful for better decision making. So yeah, that's the case in this picture also. So these are again ones related to segmentation, and yeah, so a deep learning model can give this additional information. Okay, if it is uncertain about some regions where it is doing this segmentation, then it seems that it's a bit uncertain in this region, for this picture, maybe like this region, and maybe in this case it is very certain about most of the regions. Yeah, so this additional information about uncertainty will be helpful in decision making. Like, for example, if there is some picture for which it is very, very uncertain in most of the regions, then instead of letting this model taking a decision, you can ask a human to take a decision, and that can prevent any kind of fatal accidents, possibility of accidents. So here are some experiments that we have conducted, and we found that, okay, these kind of deep learning models, okay, there are several metrics also one can use to capture the uncertainty modeling capability of models, and we always find that Bayesian deep learning models have a better uncertainty modeling capabilities. But you can just keep this for the time being. So another area where again these Bayesian principles can be useful is something called the Bayesian optimization. So many times you may want to optimize some function, and the function can be very complex function, which may not have a closed form expression. So one typical situation arises in engineering discipline, like mechanical engineering or several other engineering disciplines, where they use simulation to produce some output. And this simulator is associated with some parameters. And they want to optimize these parameters so that they will end up getting the desired output. Okay? So this kind of situation happens in many times in physics and engineering disciplines, where there are some simulators they are using to simulate something. And the simulator is associated with some parameters, and they want to optimize these simulator parameters so that they will end up getting the required outcome. So recently, yeah, I saw some I was working with some faculty from physics on, he's developing some laser technology where he wants some required outcome by optimizing certain parameters. So in these situations, the outcome, you cannot express that outcome as a mathematical expression of these parameters. Okay, there are some complex processes through which this outcome is generated, and you cannot have a mathematical expression of this outcome. You cannot write this y outcome y is equal to some f of parameter theta. That is not possible in these situations. So, so if you want to get optimal value of these parameters, something like a gradient descent, etc. won't work, because you cannot compute the gradients. You cannot even write the functional form in a closed form. So you cannot write, compute the gradients of that function with respect to the parameters. So there are situations where you want to do optimization of some function with respect to some parameters, but the function itself, you may not be able to write it in some closed form, or the gradients, you cannot compute the gradients for the function, so gradient descent, etc. won't work. And it can happen, this function itself will be very costly to compute. So you cannot evaluate the function so many times. For example, this simulation, they may take some time to produce the outcome. Okay? It can maybe like an hour or 2 hours or more than that. So the function itself will be costly to compute. If the function is not costly to compute, what you can do is that you can try out different values of theta, the parameters, and you look at all possible outcomes and choose that value of theta, which is having the optimal outcome for the function, right? But that requires you to evaluate this function several times. So evaluating the function itself will be very costly. So now the problem setup is that you want to find out the optimal values of the parameter by evaluating the function minimal number of times, very small number of times. So how can you do that? How can you get an optimal value of parameter without too many function evaluations or without using gradients of functions? So that is a kind of a problem situation that is addressed majorly using this Bayesian optimization. And the idea is, again, based upon the Bayesian principles. Maybe you start trying to approximate this function by using some observations, and then you try to query this function for some values of the parameters, so that you try to get a better approximate of this function after every step. So how do you get a better approximation of the function with minimal number of function queries? And that's what is addressed using this Bayesian optimization, which is again based upon Bayesian learning principles. So we'll be having a lecture on Bayesian optimization. We will discuss this in detail. And of course, we all know that, okay, we need data to train deep learning, machine learning models, but annotation of data is very, very costly, very time consuming. So especially if you look at complex tasks in vision and NLP, like object detection or like parsing, all these, or sequence labeling. So all these requires you to annotate data, but data annotation is very costly, time consuming. So you don't want to spend so much of money and time annotating too many data, because some of these data will be similar to each other, and then annotating them again and again will not make sense. So you want to choose some set of data points from the collection of your data points to annotate, so that you will get a maximum coverage of all the different situations that you will be encountering, the model will be encountering. So how do we actively choose the data points to annotate so that we will end up learning a very good model which will be able to predict well? Okay? So that is the philosophy behind active learning. And for active learning also, these Bayesian models will be very, very helpful and useful, as it can provide some estimate of uncertainty. That uncertainty information can be very, very helpful in deciding which data point to annotate now, so that we can reduce that uncertainty the most. Yeah, and there are some other situations like, online learning. Okay, so we will keep getting data over time, and we don't want to retrain the entire model as we get new data, but we just want to update the model, and that kind of online updation is easily possible for a Bayesian deep learning model or Bayesian learning paradigm, because you assume this prior posterior belief updates. So assume that you get some data, you you assume some model M, and you have some prior belief over the parameters of the model, and based upon this data that you have received, you update that prior belief and obtain some posterior belief. Now, after some you get some new data. So when you get new data, you can consider this posterior belief that you already have as your prior belief, and then you can update that with respect to the data that you have received and get a new posterior belief. You can keep on doing that. So it is easily amenable to such kind of a streaming setup, and you can easily make these Bayesian deep learning or Bayesian learning models work for a streaming and an online setup. So, and it can be useful for other kind of learning problems and learning setups like continual learning, where you will be seeing different tasks in a sequence, one after the other, and you want to keep learning from one task to another task without forgetting the previous task. And Bayesian learning paradigms can be quite useful to address these kind of situations. And obviously, we have a lot of other models which can be, which are used in generative AI, right? For example, you want to generate some images or generate some text, especially for generation of the images. If you want to have some sort of a variety over the image generation, people have found that considering some Bayesian modeling philosophies could be useful, and consequently people use variational or autoencoders or diffusion models, all that for this purpose of image generation. Yeah, so this is majorly what we'll be doing in this course, and these are a brief overview of the course content. Yeah, so we look at, well, I already covered maximum likelihood estimation, math estimation, etc. in the foundations of machine learning course, but I think many of you haven't taken the foundations of machine learning course offered last semester. So maybe should I cover that or not? You have taken, right? Yeah, so let's see. But we mainly focus on Bayesian estimation of the parameters, but maybe just introduce a bit ML, map estimation, and then majorly focus on the Bayesian estimation of the parameters. And then we look at Bayesian linear regression, Bayesian A-based classifier, logistic regression, and unsupervised learning techniques also, like Bayesian Gaussian mixture model, and all these Gaussian process, latent directional allocation, which are some of the Bayesian models. And then we look at these inference techniques like Monte Carlo methods, sampling methods, and Laplace approximation, variational inference, expectation propagation, all those inference techniques. And finally, we look at these Bayesian deep learning models also. So these are some of the references we are going to follow. Christopher Bishop, Kevin Murphy, which is probably something you are all familiar with. And there is another book which is specifically for Bayesian data analysis, which is also very popular, which is known as Bayesian data analysis by Gelman and Carlin, etc. So yeah, these three are the major books we are going to follow for the course. And there will be some research papers also I will be sharing, which you can follow. Yeah, course evaluation. Yeah, this is tentative course evaluation, like 2 exams, 40%, one assignment, like 20%, and one project, which is like 40%. Sure. Okay. Any questions? So those who are online, any questions? So regular students are required to attend the class physically, own class, not online. So this online classes are only for working professionals or taking the classes outside IITs.
Sir, one question regarding this material. So how would you be sharing this? Is it on Google Classroom or on the Teams?
So we don't have any Google Classroom. We are using Teams Classroom. So it will be shared in Teams
Okay.
Classroom.
Yes, sir. Thanks.
So I have shared the code to join the Teams Classroom.
Yeah.
So hope you have received that code.
Yes, sir. And these exams are for MDS batches. Will this be like taken? Can this be taken online or will this be offline?
Yeah, we'll
exams?
decide that. I'll let you know.
Okay, sir. Yeah, thank you.
Okay, sure. So then, yeah, we'll wind up for today and we'll meet again Friday.
Okay, thank you, sir.
Sure, bye.
Yes, sir.
So how can you share the recording of videos?
It will be available in Teams.
Okay, thank you, sir. And slides?